So in this video, I want to go over a neat trick to understand reaction quotients. So let's say we have this very simple reaction where this compound A turns into compound B. So this very simple reaction. And let's say this reaction happens to have a KQ of 1. So we know this reaction reacts, and once they reach equilibrium concentrations, we plug them into this KQ equation, and we would get 1. So what does that tell us? That tells us at equilibrium, there's the same amount of B and A. So we know at equilibrium, we have even amounts of A and B, so that's why this ratio turns to 1. So that's what this KQ of 1 tells us about this reaction. However, what if we're not at equilibrium? What if we want to find the reaction quotient and we're not at equilibrium? Well, again, we know we plug in the current B concentration over the current A concentration, and that gives us the reaction quotient. So we know at equilibrium we have even amounts of A and B, but what if instead maybe we have 10 moles of A and maybe 1 moles of B? Then we know we're not at equilibrium. We know at equilibrium we have even amounts of A and B, because again the ratio is 1. But now we're not at equilibrium. We're not at equilibrium, we don't have even amounts of A and B, so we know they're going to react. We know they're going to react where this reaction goes forward, creating more B. So the concentration of A will decrease, the concentration of B will increase, and eventually they'll get to even amounts of A and B. And once they're even amounts of A and B, they've reached equilibrium, where the reaction rate going forward is the same as the reaction rate going backward. And therefore the concentrations stay even, and they stay the same, and therefore we're at equilibrium. So we can clearly see we're not at equilibrium. So we would have a reaction quotient. What would the reaction quotient be? Well, again, we would have B is 1. The current concentrations, at this current concentration, B would be 1, A would be 10. So now we would have a reaction quotient of 0.1. So we know in these conditions, we have a reaction quotient of 0.1. We know we're not at equilibrium, because only when the reaction quotient equals the equilibrium constant are we at equilibrium. So we're clearly not at equilibrium. So we know this reaction will change. We know this reaction isn't at equilibrium. So now we might ask, which direction is this reaction going to go? Is it going to go forward or is it going to go backwards? And this is a simple example. We can clearly see it will go forward, but sometimes it's more complicating. When we have multiple reactants and products with different coefficients, and it can get complicating. But here's a very neat, simple trick that you can use to always determine which way the reaction will go. What you do is you create a number line. So you create this number line, and then in the center, you put the KQ. You put the KQ constant. So that you put the KQ, and we know the KQ happens to be 1. This example, the KQ happens to be 1. Now what you do, so now that you know what the reaction quotient is, the equilibrium constant, you plug it in and you put it at the center. The KQ is at the center. Now you solve your reaction quotient. So now we solve our reaction quotient, and now we see we have a reaction quotient of 0.1, which is less than 1. We know if we create a number line, this is less, so 0.1 is less than 1, so we would put the reaction quotient somewhere here. The reaction quotient would be down here, and again, it's at 0.1. So now we've done it. We know the equilibrium constant we put in the center. And then if the reaction quotient is less than 1, if it's less than 1, then we put it we put it essentially to the left. So now we know the reaction quotient wants to go towards equilibrium. We know the reaction wants to go towards equilibrium because we're not at equilibrium, so we know this reaction wants to go towards equilibrium. So we can see based on this number line, the reaction quotient wants to go to the right towards equilibrium. So a neat trick is whenever that's true, and if the reaction quotient is going to the right towards equilibrium, then we know the reaction is going to the right towards equilibrium. So again, whenever the reaction quotient is less than the KQ, the reaction is going to the right towards KQ. So we know this reaction at these current reaction quotient concentrations, we know must be going towards the right towards equilibrium. And we know that makes sense, because we know this reaction should go towards the right towards equilibrium, because as it goes towards the right, it creates more B relative to A, so it's creating more, as it goes to the right, it's making more B relative to A, so as the B concentration increases and A concentration decreases, this reaction quotient value gets closer towards 1, So that's just a neat trick you can use. That's a very simple trick you can use. But now, let's say we have different reaction quotient concentrations. Let's say now we have current concentrations where instead we have 1 molar of A. Let's say we have 1 molar of A, and let's say we have 10 molar of B. So now we have these reaction quotient concentrations. So what if we plugged in these reaction quotient concentrations here? Well, again, we have 10 molar of B, and and we have 1 molar of A. So this would give us a reaction quotient of 10. And again, we're still not at equilibrium. Only when the reaction quotient equals the KQ are we at equilibrium. So we see the reaction quotient is not at equilibrium. So again, however, we can use our neat number line trick. So again, we take the reaction quotient, and we know the reaction quotient is now 10. It's greater than 1. So on our number line, it would be to the right. It's greater than 1. So now what do we notice? Now we know this reaction quotient wants to go towards the left towards equilibrium. We're not at equilibrium. We see we're not at equilibrium. So now the reaction wants to go towards the left towards equilibrium to get to equilibrium. So therefore we know this reaction, this reaction quotient concentration wants to go towards the left towards equilibrium. So again, if the reaction quotient is higher than the KQ, it wants to go towards the left, towards equilibrium. So we know a neat trick we can use is that always means that this reaction wants to go towards the left. They both want to go towards the left, towards equilibrium. And we know that makes sense, because as it goes towards the left, it makes more A and there's less B. So there's more A is made and there's less B. So this value will drop and eventually it'll keep on doing this until this value eventually gets to 1. And once it's at 1, when we have even amounts, then we're at equilibrium. So this is just a neat trick, this number line trick that always works, where you find your KQ, and if our KQ was 18, just something arbitrary, then in our center would be 18, and then we would find our reaction quotient, and if our reaction quotient was left, we know the reaction is going to the right. If the reaction quotient was greater, than our KQ, it would go towards the left. So again, that's just a neat trick that you can use. And again, the further away the reaction quotient is, the more it wants to go towards equilibrium. And this is something you'll learn later in Gen Chem. But once the reaction is at equilibrium, there's no free energy in this reaction. Once it's at equilibrium, so let's say we're at equilibrium concentrations, then there's no free energy released going in either direction. There's no free energy because we're at equilibrium. However, when we're not at equilibrium, and let's say we have 10 molar of A, and so we're not at equilibrium, then there is free energy. Because again, we saw when we have 10 molar of A, we had this reaction quotient, so the reaction is not at equilibrium and it wants to go towards equilibrium. So as it goes towards equilibrium, it releases free energy. Or depending on the situation. But again, so that's something else that's a little more advanced. But in this video, I just wanted to focus on the KQ and reaction quotient. But the point is, the further the reaction quotient is from KQ, the more free energy there is released going towards the KQ. And if the reaction quotient is very near the KQ, then there's very little free energy released. But when the reaction quotient is at KQ, there's no free energy released in this reaction.